Okay, there we go. There. I'm I woke up late today, so that's gonna throw off my whole day, I think. It's just how it is. All right. Oh boy. Oh boy. So let's see. Oh, I have to apologize. I finished looking at and giving feedback on your reports. I'll be honest, I completely forgot about them because you guys are so self-running. It's your fault. I blame you. No, I apologize for that, and I didn't have time to post the feedback this morning, so I'll do it after class. So you can have a look at that. Nothing crazy. I'm generally pleased. So let's see here. Today, well, let's do a little bit of review. Let me bump this down so I can see. Not really review, more of a commentary or a recall what we did. So last day we did confidence intervals. And we talked about sampling as well. So we talked about confidence intervals, and we established that if I have some sort of point estimate, in this case p hat, so a sample proportion, then I would build a buffer around that. That buffer is called the margin of error, and we use Z star, which is our critical value. We talked about how to find Z star, but in general, we're going to use 2 for a 95% confidence interval. And if you want to get more precise or a different confidence level, you'd have to use Excel, right? So traditionally, we have tables and things, and I just want to try to shake that as much as we can because we have software now. And so for other confidence levels, we use Excel. I mean, technically, 2, this 2 is really 1.96 if you want to get really picky about it. So either one is fine. Okay. So we take Z star, so we move out 2 standard errors around p hat. Now the standard error of p hat is p hat q hat over n, where q hat is just 1 minus p hat. I mention that over and over again because that's usually a question that I get. What is Q? I know, weird. And then we talked about sampling. Sampling from an infinite or a finite population. Sampling from, I'll say, finite and infinite populations. It's infinite, but helps me spell it. Right? Different ways that we could do that. Can't remember if that was last day or the day before. I think that might even be last week. That was last week. Yeah, right? I think I must have flipped through the notes and been reminded. But anyways, it's a good reminder. And then, so was it last week that I assigned you the central limit theorem Excel exercise for the Friday? I think so, right? Where you have to use the sampling function. So that's one of the ways that you can randomly sample from a finite population, right? We have a finite population, we have it all there, and then you can use that sampling function in Excel. There are lots of other ways that you can do it, but that's one of the ways. Okay, so last day, then I just have to think about, we did just confidence intervals. Maybe I'll do this in a, this was actually last week. Oops. Last week. I'm not going to erase it. It's still review, I guess, technically. So today, let me remind myself. Sorry, guys. Check the conditions. We built the interval. Oh, good. And then we interpreted the interval. So almost kind of the most important part of building a confidence interval, the math isn't hard. The concept itself, once you've kind of taken a step back and thought about it, is not hard. But the interpretation is very, very important, right? Because we're reporting this information. It's our job to communicate what this information means. And so in general, we're going to use this interpretation. So we're 95 or whatever percent confident. 95 is the default. So that's why I have 95. We're 95% confident the interval from here to here, and then captures the parameter, where the parameter is just rewording the question as an answer, because I'll have to tell you, make a confidence interval for this, right? And then, so in this case, the question was construct the 95% confidence interval for the true proportion of American Facebook users who think Facebook categorizes their interests accurately. And then we interpreted that, but that whole last part is the parameter, the thing that we're trying to capture. And so today we're going to move into hypothesis testing, and we'll just introduce it. I'll say that's the end of the review. Hypothesis testing, which I'll abbreviate HT, because that's annoying to write. And hypothesis testing is a formal framework for establishing significance. Okay. So maybe I'll put it down here. Hypothesis testing is a formal framework. Oops. For establishing significance. Okay. As an example, right? If I work in sales and I'm up for a promotion, I might want to prove that I sell significantly more than my coworkers, right? So in order to use that word significantly, we have to do a formal hypothesis test. And so I sell significantly more than my coworkers. That says coworkers, sorry. It's the significantly. Using that word requires a formal hypothesis test. Requires a formal hypothesis test. And you can say you sell more, but in order to say that you sell significantly more, then you have to use a hypothesis test. Okay? I'm going to clean up this coworkers. What a mess. Not much better. Oh, well, maybe it's co-workers. I don't know. Doesn't matter. Oop. Mess it up even more. Okay. In terms of a proportion, right? Because if we're talking about the number of sales, that's numerical information, right? But we're going to start with categorical information. In fact, we're going to start with one sample proportion. And so as another example, right, the proportion of voters voting in favor of this candidate or of some candidate is a majority, or the majority of voters are going to vote for this candidate. There's some implied information there. And maybe I'll bump this down just another example. The majority of voters will vote in favor of candidate A, whatever. It used to be funny to talk about Trump, but now it's not so funny anymore when we talk about voting. And so let's just call it candidate A, right? So what we're gonna have, right, is, okay, what does a majority mean? A majority means more than 50%, right? And so that's technically, so there's some wiggle room, because if I say more than 50, then it can't be 50. But yeah, technically 51, but we're gonna use 0.5 as the cutoff at 50%. And so here we're gonna say more than 50%, but not including 50. And we'll see that, but okay, so what we're gonna have is, okay, so voting in favor of candidate A, they either vote in favor or they don't. And so here, oh, my screen just feel like it did something strange. Let me just go check on the Zoom here, just briefly. Okay, looks good. Sorry, a little intermission. I don't know why I don't know, did something. So voting in favor, the outcomes are either yes or no. You could include a don't know, but we'll just focus on the yes, no, which means that it's categorical. And so we're going to be talking about a sample proportion. So P hat is the sample proportion who say they're going to vote yes. Sample proportion in favor of candidate A. Now, to work out just kind of hypothesis testing intuitively, I want to just show you a scenario, and trust your gut. You do know what it is, and then I'll just kind of talk you through why it is the way that you think it is, and then we'll make the connection that way. So hypothesis testing is going to go something like this. So if we have a normal distribution, which of course we're going to have to check the conditions for, make sure that they're satisfied, but let's just ignore all that for now. What we're going to have is, in this scenario, right, 0.5, any sample proportion greater than 0.5, right, would be considered a majority, right? And so what if I said, okay, if I draw something maybe here, let's say this sample proportion, just without having any values or anything like that, just looking at that, is that significantly different from 0.5? Not really, right? Because it's very close to 0.5. Here, in fact, anything that's kind of in this bulk of the data is not considered significantly different, right? It's like saying, okay, so here I'm pressed up against the desk. I'm sitting at the desk, obviously, because I'm at the desk. But then if I scoot back a little bit, I'm still allowed to move around the desk and still, you would say, oh, where's Emily? Oh, she's sitting over there by the desk, right? And so there's this wiggle room where kind of the bulk of the data, in fact, the central 95% is generally considered not significantly different from the center, right? And so here we kind of have this, what can I do here? Kind of a rough guide here. This is not significantly different from 0.5. So we have this wiggle room and it's quite large. In fact, it's 2 standard errors, right? If it's 95%. Oh boy. And so that's kind of what you're relying on. So initially I just gave you this line, right? And I said, hey, just trust your gut. Is it significantly different? It's different, sure, but it's not significantly different, right? And so that's what we're going to be leveraging. Now, if you were just looking at this number line, you might say, okay, it's not significantly different because it's not very many standard errors away from the center, right? It's not very many standard errors away from 0.5. That's good, but that's really hard to communicate, right? And so it's hard to communicate to someone who has not done statistics or doesn't care about it, or is your boss and they are paying you to know about it and they don't want to know about it. And so what we do instead of talking about how many standard errors away you are from the center, this hypothesized proportion is what we're going to call it later. Okay, is we're going to say, okay, the probability of seeing something more extreme, right? And so here, that's going to be the area to the right, right? More extreme, if you're above 0.5, has to be this area. And so from here, this area is the probability of seeing a p-hat as extreme or more extreme. What are we assuming that the population proportion is 0.5, right? So assuming that it's centered on 0.5, then this is the probability, and we can find that area under the curve, right? We know how to find probabilities associated with a normal distribution because we have the z-score, and we've done work with the normal distribution. And so I'm going to add here, it's a probability of seeing a p-hat as extreme or more extreme, assuming the population is centered on 0.5. Yeah. And so that's what we're going to develop today, is just linking these areas to a z-score, or rather finding a z-score to find the areas, right? And these probabilities of seeing something as extreme or more extreme, which is always going to be the area in the tail. Now, let's just kind of take a step back and say, okay, what if I had a proportion, a sample proportion below 0.5? Well, first off, it's going to be really hard to use something like 0.4 to prove that it's more than 0.5. So that's not going to work, right? But let's just ignore this for a little while, right? If I had something, so a sample proportion that's below 0.5, then something as extreme or more extreme would be the area in the tail, but in the lower tail, right? And so it just depends on which side of the center you're at to find that area. This area is going to be called a p-value. Okay, it gets kind of tricky because we have so many p's now, right? We have the sample proportion, we have the population proportion. We're going to introduce a hypothesized proportion, okay, today, and then this is the p-value, which is different in the sense that it's strictly a probability, right? And so it's the probability of seeing something as extreme or more extreme. If I drew another scenario, right, wait, centered on 0.5, right? So I hypothesize that it's centered on 0.5. And then I have this sample proportion out here. Okay. Now all of a sudden you're thinking, okay, that's probably significantly different from 0.5. It's very, very into the tails, right? In fact, let's see if I can draw this better. Start over. Oh. Could spend all day drawing normal distributions. Here we go. Say that. Yeah. So now you're thinking, okay, well, that looks like more than 2 standard errors. More than 2 standard errors from 0.5, right? Because it's quite into the tails, just intuitively, right? We don't have any values or anything like that, but just looking at this, it's quite far into the tail. And so then we're going to say, okay, it's far from 0.5. How we're going to communicate that, though, is by saying the probability, right? Because the further that you move away from 0.5, the probability of seeing something as extreme or more extreme just keeps getting smaller and smaller and smaller, right? And so here, and I shouldn't have used pink here, so I'm going to change it to green, maybe there, because I used, so now the p-value is very small. In fact, how hypothesis testing is going to go is just if the p-value is small enough, we need some threshold, right? Some way to say, well, what's small enough? Okay. And we're going to use 5%. So if it's less than 0.05, right, then we're going to say, yeah, sure, this sample proportion could happen if the population proportion was 0.5. It can, but the probability of it happening is very, very small if the center is actually 0.5. So what's more likely to have happened is that I pulled this sample from a different proportion, right? Or from a different population, not centered on 0.5, but probably centered on something larger than 0.5, right? And so one of the key elements here is that we have to assume that the center is 0.5 before we can establish that, oh, okay, that's actually unlikely, right? Given my sample proportion, it's really far away from 0.5. In fact, the probability of seeing something that extreme is very, very small. And so then I can reject that hypothesis and I can say, okay, that's unlikely to have happened, right? It can happen, right? There's this probability that it actually can happen. You might just have a weird sample, right? But that's why we have to be so picky about our wording later. Yeah? But where we're going to start is just establishing there are going to be 4 steps to hypothesis testing. Now, you can generate more steps if you want. I just like to have 4 because I think it's nice and manageable, easy to remember. And so there are 4 steps to hypothesis testing. I'll write it out. So first thing I want to do is just kind of go through and establish the basics just theoretically. I suspect, just from other times that I've done this, that we won't have time to do an example, so we'll do an example next week, but that's okay because we need these steps. Now, what's really nice is once we have these rules, kind of rules of the game, then we can play all the games, right? So it's worthwhile kind of spending some time and just talking about what each step is, and then we can apply it to all the different types of scenarios. And so that's really nice. So step 1 is to state the hypotheses. We're going to have something called the null hypothesis, which is your initial hypothesis. It's a statement of no change, hence the null. Okay, and so the hypotheses are going to look like this. So this is an H subscript 0, and this is the null hypothesis. This is going to be a statement of no change. Now, because it's a statement, we follow it with colons. And so here, it's a statement of no change. Okay. It's going to be a statement about the population. Remember, the goal of hypothesis testing, just from the past few days, is to learn about the population. So we have sample information, but we want to ultimately learn about the population. And so the population parameter that we're talking about in this case is going to be P, right? I want to learn about the population proportion. Want to learn about the population proportion. And so this is going to be for the one sample proportion case. And for each type of question, I'm going to introduce you to what the null hypothesis would be. And so I'll give those to you, but then sometimes you have to find values to plug in. And so here I want to hypothesize about P. Now, a statement of no change means that you're going to have an equal sign here, right? If there's no change, then it's equal to some value, right? We only have one sample, and so it's going to be equal to some number. Now, if we refer back to this example, right? If I want to prove that the majority of voters are going to vote in favor of candidate A, I want to prove that it's more than 0.5, right? But what I have to do in order to do that is to assume that it's 0.5, right? And establish that the probability of that happening is very small. And so it's more likely that it's more than 0.5. So usually the thing that we're trying to go for is the alternative hypothesis. Okay? And so in general, we're going to have, and this is a P subscript 0 or a P naught. Okay? And I'll highlight that and put it down here. P naught P naught or P null, but I think that sounds weird. So P naught is the value that we want to compare our sample proportion to. And so it's going to be a value from the question. So depending on the question, you'll get your value there. And it's P naught because it's in the null hypothesis. Right? And so P naught is the value from the question you want to compare your P hat to, right? Your sample proportion to. You know everything about your sample, and so now you want to try to use it and say, okay, it's significantly more than 0.5, for example. So just as a, for example, we had a null hypothesis that P is equal to 0.5, right? We have to assume that the population is centered on 0.5 until we have proof otherwise. We have to assume the population is centered on 0.5, oops, until we have proof otherwise. So that's going to bring us to the alternative hypothesis. The alternative hypothesis, like I said, is usually the thing that you're trying to prove, right? Sometimes it's not. There are scenarios where you're really hoping that the null hypothesis is the more likely one. But the alternative hypothesis, I use HA. I'm curious to know what Allison would use. But I'll use HA for now. Some other options are, or lowercase a or H1, depending on what field you're in, right? 0 and 1 kind of makes sense. I use a capital A just because I think it makes it more obvious, but this is the alternative hypothesis. Oops, not caps. This is usually the statement we're trying to prove, right? Usually the statement we are trying to prove. So again, it's a statement. So our alternative hypothesis is this. Now, one key thing to remember is that, okay, it doesn't make sense to talk about anything but the population proportion still, right? And also how it relates to this hypothesized proportion. So these two things just drop down, and the only thing that changes is the inequality, right? Or equality, I guess, in this case. And so we have P, how it relates to P naught. And the only thing that changes here is this sign. Only thing that changes from H naught. In fact, we have three options, right? We could hypothesize that the proportion is less than some value, right? More than some value is what we saw, right? If I want to prove that there's a majority, then I want to show that there's more than 0.5, right? And then as a default, just not equal to. If you're not sure which direction you care about, or maybe you just don't care about it, you just want to know if there's a difference, then you would use not equal to. And so we could have, there are, the inequality in HA can be I'm struggling because I have a page break and I want to keep it on, but I've really crammed it in here. Can be less than, right? Less than. It can be greater than. Or it can be not equal to. So if they're different, or if there's a difference, right? Is it different from 0.5? And so in our scenario, right, for our example, we would have our null hypothesis, we said, is P is equal to 0.5. I have to assume that it's 0.5, right? But then my alternative hypothesis, if I want to prove a majority, then really what I'm trying to show is that P is greater than 0.5, right? A majority. And so those would be your null and alternative hypotheses. So even though I've talked a lot in this step, I know we're only on step 1, all you really have to do here is this, right? And so there's a lot of components and things to think about, but the only thing you have to do in this step is this. You don't even have to say the majority, it's just this. Okay? But I want to talk a little bit more about this inequality, because the inequality in your alternative hypothesis is going to determine what the p-value is, what area you're going to find. And so we have these 3 scenarios. First, if the alternative is that p is less than p naught, just in general, or if it's p is greater than p naught, or finally, if p is not equal to p naught. I will make a note here that the not equal to should be your default. Okay? If you're ever unsure, then, or even if you are sure, and you could argue that you just want to know if there's a difference, it's just a little bit safer because it's harder to reject the null hypothesis later, which we haven't talked about. And so I'll reintroduce that. But the not equal to is going to be your default. Okay, so in terms of our normal distribution, oh, I should have just copied and pasted 3 kind of wonky normal distributions. They're all going to be centered on P naught, right? We do all our testing assuming that the null hypothesis is true. Well, what's the null hypothesis? The null hypothesis is that P is equal to P naught. So we assume that it's centered on 0.5 or P naught in general. So then what happens is, well, if you want to prove that the population that you drew from actually comes from a population that's centered on something less than P naught, well, you better hope that your sample proportion is also less than P naught, right? That's a good place to start. Okay. So then the area that you'd want is the area, the probability of being as extreme or more extreme, which is the area in the tail, right? And so here, right, if P is less than P naught, you're going to want the lower tail. If P is greater than P naught, then again, you can't use 0.4 to prove that it's more than 0.5, right? That's hard / impossible. And so you better hope that your P hat is somewhere larger than P0, right? In order to get anywhere, right? And so then the area that you want, the P value, is going to be this area in the upper tail. Yeah, so what you want is you want to find this area, and that's going to be your P value. I'll write that because that's good. So the P value is going to be those areas, depending on what the alternative hypothesis is. Now, what's tricky about the not equal to is you don't care which tail it's going into, right? And if we think about, okay, so you've collected one sample, you're only going to find one sample proportion, right? And so that sample proportion could be down here, or it could be up here, right? And so you're only going to have one of the scenarios, but that's okay, because what we do is, let's say you found your sample proportion down here. What we do is we just replicate it in the other tail. So you just multiply the lower tail area by 2 to replicate it in the upper tail. So then here, and I'll say to find the P value for HAP not equal to P naught, and I'll highlight the thing that I'm talking about, the not equal to. We find the area in one tail, in one tail, and multiply it by 2 to replicate it in the other tail. Yeah. So that's a little bit tricky, but once you kind of get the hang of that, then you're okay, right? You just need to multiply it by 2, and you've got the norm.s.inverse command, the norm s.dist command to find the areas in the tail, right? And then you can just multiply it by 2. Let's see here. These little guys, I'm trying to find a color I haven't used. Maybe I didn't want to use, oh, maybe purple. That's nice. These are called one-sided or one-tailed tests, right? Because you're only interested in one of the tails, one of the extremes. Whereas this is called a two-sided or a two-tailed test. I use them interchangeably, just depending on what sounds better. Oops, two-tailed test. Right, it's a hypothesis test, and so but this two-sided test is the default. Okay, good. Why is it the default? Let's think about that. We said, okay, if the probability, so if the area in the tail, the p-value is small enough, then we can reject the null hypothesis and say it's more likely that the alternative hypothesis applies, right? And so now, if I find the area in one tail, and then I multiply it by 2, I'm making that p-value bigger, right? which makes it harder to reject H naught, okay? Which is what we're working towards, right? There's evidence to reject H naught, and so, right? Or maybe there isn't evidence to reject H naught if they're not far enough apart, the sample proportion and the hypothesized proportion. Okay, how about step 2? Step 2 is technically calculate the test statistic. Now, I find that that's kind of boring to think about. It's true. Calculate the test statistic. I call it do the test. I think it sounds cooler. Do the do. So do the test. And I'm being generic here because the test statistic is going to change. So for now, the only test statistic that we know is the Z, right? Z tells us how many standard errors something is away from the hypothesized center, right? And so that's what we're going to use now in the beginning. And then we'll introduce some other test statistics, right? But the test statistics in general are that measure of distance, right? How far is your sample information from your hypothesized information? And so your test statistic is a measure of how far your sample information is from the hypothesized population. Well, I know what I forgot. In here, before step 2, we really should check the conditions. I'm going to kind of ignore that, right? And I don't want to talk about it today. I don't want to talk about it. And so here, check the conditions for the central limit theorem to apply. Otherwise, we don't have a normal distribution. We can't calculate a Z, blah, blah, blah. But we're going to assume that that all checks out. And so we're going to skip today. Right? I don't want to introduce all those rules because I want to keep it just hypothesis testing. CLT, there. But that's where we should check the conditions. You can see I totally forgot about it, so I never do it. Okay. So the test statistic is a measure of how far your sample of information is from the hypothesized population. Now, for one sample proportion questions, which is what we have in our example, right? We have Z, which is what it is going to be a calculation of. We're going to have P hat. How far is it from P naught? Depending on the spread of P naught, right? And so we're not going to talk about the spread of P hat. We're going to talk about the spread of P naught. And so what happens is we've got P naught Q naught over N, square rooted. And so for one sample proportion, right, Z tells us how many standard errors P hat is from P naught. The standard error of the hypothesized proportion, or hypothesized population. Population proportion, I guess, but that's okay. In general, the hypothesized population. So this changed, right? P naught, and maybe the second highlight is too much. The P naught, we're used to seeing P hat, Q hat over N, and then square rooted, right? That's the standard of P hat, standard error of P hat. But now that we're talking about the hypothesized population, we need to know the spread of that thing. And so now this is the only change here, right? But you have P naught from your null hypothesis. And so the calculation is essentially the same, right? You've got a P times a Q over N square rooted. And so Z, right, now we can calculate probabilities associated with this Z, right? This Z tells us how far P hat is from P naught, right? In terms of the number of standard errors. But like I said, that's really hard to communicate to someone who doesn't want to talk statistics, which is everyone. And so what we do in the follow-up step is we clean this up a little bit and we talk in terms of probabilities instead, right? And it's just the nicer way to communicate. Put it on a fresh page here. Step 3 is find the p-value. And I will make a note here, right? We can use the normal distribution and the z-score to find the area, potentially areas if we have a two-sided test in the tails, potentially two tails. Okay. Which is the p-value. So find the p-value. Is the next step. Now, this is where a lot of people are thrown off because you have to go back to your alternative hypothesis and figure out which area in the tail that you need, right? And so depending on this depends on HA, the alternative hypothesis, right? And so you have to go back to step 1 and figure out which area in the tail you need. We need to go back to step 1 to figure out which areas, potentially 2, in the tail we need. Okay. So here, right, depending on what our alternative hypothesis is, that's going to determine which area in the tail we want. And I'm going to copy this. Paste. Shrink it up a little because we already have it. All right. So depending on if we have a one-sided or a two-sided test, right, that's going to help us figure out which area in the tail that we need. Right? In our example, right, we have a population, a hypothesized population centered on 0.5. Now, that means that our p hat, our sample proportion, should be somewhere up here, right? And so we can calculate the z of p hat, right? Without numbers, it's hard to do, well, impossible even. But it just tells us how many standard errors p hat is from 0.5. right? And so then we wanted to test our null hypothesis that p is equal to 0.5 and the alternative that p is greater than 0.5, which means that my p-value is the area in the upper tail, right? Just to match the alternative hypothesis. Okay. I'll underline. I think I've been underlining. Yeah. So finding the p-value, you know how to do because we've already done a lot of work finding areas under the curve for a normal distribution. And so that's nice. That's nice and familiar. And so now what we're going to do is we're actually going to do something with this area, right? And so what we're going to say is in step 4, which is your conclusion is always going to follow this format. Okay, so there are only 2 options, right? We said, okay, if the p-value is small enough, then I can reject H naught, right, in favor of HA. Or the alternative option is the p-value is not small enough, right? And so it just hinges on how big the p-value is compared to some threshold. Now I said we're going to use 0.05, and that's it for this course. Now, kind of traditionally, we would play around with 0.01, 0.1, but those are all kind of common significance levels. Now, a significance level is established at the beginning of a study, and the default of 0.05 is generally fine. Now, you would want to decrease it if rejecting the null hypothesis is very expensive, for example, and that can mean expensive to some group or financially, or just kind of if there's a lot of implications. Okay? And so here, if the p-value is, and I'm going to say small enough, and that's small enough, I'm going to clarify, less than the established significance level, the established significance level. The significance level is also called the alpha level. Okay, so less than the established significance level, and the default alpha is 0.05, right, 5%. So if the p-value is small enough, so in our case, less than 0.05, yeah, we have enough evidence to reject H naught. If you're rejecting H naught, then you should probably say in favor of what? In favor of HA. And then, of course, what does that mean in terms of the question, right? So then you state your conclusion in terms of the question. But I'll hold off on writing that because I'll rewrite this blurb, the 2 different options. I just want to talk about, we have enough evidence to reject H naught. Okay, so you either have enough evidence to reject H naught, or you do not have enough evidence to reject H naught. Those are your only 2 options. It's really important that you don't say that you accept a hypothesis The reason for that is because we're allowing a 5% chance of being wrong, right? And so here, we never accept a hypothesis because we allow for an alpha level, right? Whatever you're setting your alpha level, so 5% is the default, right? So we're allowing for an alpha level, so 5% probability of being wrong, right? We're okay with being wrong 5% of the time. And we've established that from the get-go, right? We've said, okay, yeah, it could happen, but it's unlikely. Probability of being wrong. Okay. It's also really important that you don't talk about the alternative hypothesis, because we did all our testing assuming that the null hypothesis was true until we had proof otherwise. So your conclusion has to be, do you have enough evidence to reject H naught, or do you not have enough evidence to reject H naught? So your conclusion has to be in terms of the null hypothesis. Okay. And so here, the conclusion must be in terms of H naught. Since we did all our testing assuming that it was true, right, until we potentially had proof otherwise. Since we did all our testing assuming it was true until we potentially found proof otherwise. And that proof is in that p-value. Oh, little sneeze, but it went away. Found proof otherwise. I feel like just as I'm getting better, I'm getting allergies. This term. Okay. So, right, so there's a couple of notes, and these are all just important to keep in mind when you're writing up your conclusion. In fact, I just want to show you the only two versions of the conclusion that I ever want to see. Aha. So the two options for the conclusion are these. One, since the p-value of some value, right, you're going to show off that you have it, you know what it is, right? And so since and then here I'll put 1 or 2-sided p-value. This is your chance to show off all the things that you know, right? Did you know to have a 1-sided p-value, right? Or did you know to use a 2-sided p-value, right? And so, and then what is it? Since the 1 or 2-sided p-value of blank, the actual p-value. Now, in this first scenario, I'm going to make it less than the alpha level, right? Because that's kind of the more juicy version. So since the 1 or 2-sided p-value of the p-value, and maybe this part there, that's better, of the actual p-value is less than the alpha level of blank, right? Default 0.05, but it could change. If it's less than 0.05, then that it's far enough away from the null hypothesized value that you're going to reject the null hypothesis. We have enough evidence to reject H naught. And if you're rejecting it, you can say in favor of HA. And then you're going to state your conclusion in terms of the question. Right, what does that mean in terms of the proportion of voters voting in favor of candidate A, for example? Right. Okay. And maybe this part should be in blue. Well, I'll mix it up a little bit because that depends on the question, right? So on the flip side, right, do I want to? Okay, before I copy this, I want to highlight that there are 3 chunks of the conclusion, right? And so you just to remember to cover all your bases, right? The first one is to compare your p-value to the alpha level. Is it less than or is it not less than 0.05, for example? The second part of the conclusion is we have enough evidence. So either you have enough evidence to reject H naught or you don't. And maybe I'll replace this blue with pink. And then finally, your conclusion in terms of the question. So those parts, I'll make notes around those in a second, but I just want to show you that I'm just going to copy this and I'm going to edit it for the flipped version. So you'll see how little change there is. I'll use red. Option 2. Since the 1 or 2-sided p-value of whatever it is not less than the alpha level of 0.05, we do not have enough evidence to reject H naught. It's technically not incorrect to say in favor of HA, but if you don't have enough evidence to reject H naught, then that is your conclusion, right? And so bringing in HA at that point is kind of, it gets a little clunky. And so then I just want you to stop there, right? We don't have enough evidence to reject it. This is what it is, right? Or there's no evidence against it. And then, of course, your conclusion in terms of the question. So these are your only 2 phrasing options. Okay? And so this is, of course, just the flip side of the first one. So what I would encourage you to do is at this point, this is going to be a memorization thing, right? You're just going to have to memorize this statement until it becomes kind of ingrained, and then eventually it'll click, right? But in the beginning, this is a lot. There's a lot of theory here going into this, and so if it doesn't make sense, that's totally fine. Your job is to memorize it until it does. Okay. And then just remember that the flip side of it is the only other option. So in terms of the different parts, right, the 3 parts of the conclusion are these. So the first one is you're going to compare the p-value to the alpha level. Compare the p-value to the alpha level. Then the second part is you're going to use that to state your conclusion in terms of H naught. And we've already talked about why it's important that it's in terms of H naught. It's because we did all our testing assuming that it was true. And so then you're going to state your conclusion in terms of H naught, right? You either have enough evidence to reject it or you don't. And then finally, the conclusion in terms of the question. So what I want to do is I'm just going to snag a question, and it's, where is it? Probably here. Hey, this all looks familiar, huh? Skipping some stuff. Oh, well, I'll clean it up for us. Want you to try for Monday, making them try it for tomorrow. But I want you to try this question for Monday, and then we'll work through it together. Right. Obviously, we're going to work through it. But I think that is good. The only thing to note is that you'll need to use Excel to find the p-value. Right. So I'm going to do it beforehand and bring it in. Unless I can figure out how to use Excel on my iPad. But I haven't even tried. So we'll stop there. That's close enough. And I'll post an exercise for Friday where you practice making confidence intervals and interpreting confidence intervals. And there's also going to be a hypothesis testing question on there. So try it, see how it goes. And then that's good. If you have any questions, let me know. Otherwise, see you Monday. Oh, sure. I'll just stop this recording here.